This paper is about using nanotube films as polysulfide barriers for lithium sulfide batteries. Lithium sulfide batteries are a promising battery chemistry due to its high theoretical specific capacity and gravimetric energy density, and sulfur's low cost and natural abundance. However, lithium sulfide battery development faces a couple of crucial issues: rapid capacity degradation and low sulfur utilization. Long-chain polysulfides generated during the charge and discharge processes dissolve and shuttle between the electrodes, leading to side reactions and poor cycling performance. In this paper, ultra-thin hafnium oxide modified cross-stacked carbon nanotube interlayers are introduced to trap polysulfide and prevent migration to the anode. Experiments have shown improvement in long-term cycling stability, high rate performance, favorable anti-self-discharge capabilities, and suppression of lithium anode corrosion.
Okay, so just briefly, I'm going to go over what was important in our paper. So our paper was on lithium sulfide batteries, and some of the pros for these batteries is that they have high theoretical, specific, and gravimetric capacities. Also, sulfur doesn't cost that much, so it is good for large-scale fabrication. However, some of the cons are that there's low sulfur utilization within the battery, as well as capacity degradation due to effects such as shuttling. Our paper explores carbon nanotubes with hafnium oxide integrated to see if those, while added on the separator to the battery, can help to trap the sulfide chains and mitigate the problems due to shuttling.
So to go over the lithium sulfide ion battery, we have the anode on the left, which has lithium species, and the cathode on the right, which has S8 in addition to several different species. This one being the negatively charged anode, this one being the positively charged cathode. Without the buildup barrier here, we have a migration of species that is both directions for each. With this separation barrier, the sulfide ions are restricted to just this side of the cell.
So this should look really familiar to what we've been doing in class recently, as we're going to look at the transport of what an ideal cell would look like in this case. So let's start with our lithium ions. Now, it should make sense that the highest concentration of lithium ions is going to be at the anode. So let's draw our concentration up here. And then, as it flows through the electrolyte and reacts on the cathode, you'll have a lower concentration right here. This means that our flux due to diffusion will be in this direction, as it is driven by the concentration gradient. We also know that based on how the battery works and how the lithium is reacting, it is driven by the potential in this direction. Alternatively, let's look at our sulfur ions. So when we come over here, to keep electroneutrality, we will have to have our sulfur concentration be higher on the anode side. However, sulfur has a 2- charge, whereas lithium has a 1+ charge. So the concentration of sulfur would be half that of our lithium ion. So we'll draw our point right here. The same goes for the cathode. So we'll point right here. This means that the fusion will be going in the same direction as it is for the lithium ions. However, because sulfur is negatively charged, the driving force due to potential will be in the opposite direction, and so our migration will be in the opposite direction. Thus, we can see for the lithiums, the migration is augmented by the diffusion, whereas it is not for the sulfur ions. We may also later consider in class how it'll be affected when we have the polysulfide chains in our transport process.
So now I'll explain the shuttling effect that happens with polysulfides first formed at the sulfur cathode. You can see from this diagram that the shuttling effect proceeds from the sulfur cathode to the lithium anode and back through 4 pathways, A, B, C, and D. In pathway A, high-order polysulfides such as Li2S6 and Li2S8 formed at the sulfur cathode dissolve in the electrolyte. Through a concentration gradient, they diffuse to the lithium anode. Because polysulfides are an electroneutral species, transport involves only diffusion and not migration, and is only dependent on the concentration gradient. As you can see in this diagram, high-order polysulfides are much more concentrated at the sulfur cathode, where they are generated through oxidation of lithium, whereas low-order polysulfides are concentrated at the lithium anode, where they are formed through reaction. It is this reaction between high-order polysulfides and lithium ions at the anode surface that constitutes pathway B and is inherently a self-discharge process. Low-order polysulfides then diffuse to the sulfur cathode through pathway C. In the final pathway, low-order polysulfides from the lithium anode neutralize high-order polysulfides from the sulfur cathode. Pathways B and D are side reactions which reduce utilization of the active materials, decreasing the battery's coulombic efficiency. In this paper, a hafnium oxide carbon nanotube interlayer is placed next to the separator to trap polysulfides. This interlayer is selectively permeable, allowing lithium ions to transport bidirectionally, but restricting polysulfide diffusion. With pathways A and C blocked, the interlayer implicitly blocks B and D because there are no high-order polysulfides on the anode side to react with the lithium, and no low-order polysulfides on the cathode side to be neutralized.
Due to the shuttling effect that has been discussed earlier, we want to prevent this polysulfide from crossing through the separator and react with the lithium anode. So we will introduce the hafnium oxide carbon nanoparticle to coat this separator and prevent the polysulfide from permeating to the separator. But we still want the lithium ion to permeate to this separator. So we still need this. So why do we have to coat? Let's take a look at the property of carbon nanoparticle. So this carbon nanoparticle is a non-polar species. While our species of interest, they are all polar species. Therefore, when we try to do the wettability test on the carbon nanoparticle surface by dropping the deionized water onto the surface, the droplet of deionized water will form a pretty large contact angle between the droplets and the surface. In this case, it's 112.8. Such a large contact angle will lead to some property on the carbon nanoparticle surface in the battery. So this effect will prevent lithium ion and polysulfide ion from permeating through the carbon nanoparticle surface. And also it might hinder some other interfacial electrochemical process as well. Okay, in the case of hafnium oxide coating, the hafnium oxide layer here would greatly improve the surface interaction between the ionized water and the surface. So the contact angle now will decrease to only 13.4 degree. According to this excellent wettability property, it would greatly increase the quantity of active site available on the surface, and also it allows lithium to permeate through this separator, carbon nanoparticle. And it's also do exactly what we want them to do. It will be able to prevent polysulfide from permeate across the separator. However, having too much thick layer of the hafnium oxide carbon nanoparticle might not be a good idea as well, because it might interfere the charge transfer between anode and cathode. Like in this case, having 35 layers perform worse than having like 21 or 14 layers. However, as you can see, having 14 layers is not efficient as well, because it may not be able to trap polysulfide that great. So at the optimum level, 21 layers seems to be perfect, because it balances both the polysulfide trapping effect and also the availability to allow lithium to cross through the separators. And as you can see, without any hafnium oxide coating, this one CNT film, it performs worse, because as you can see here, around the first 10 cycles, the capacity will significantly decrease.
To summarize, lithium sulfur batteries have a high theoretical specific gravimetric capacity, and sulfur is relatively cheap, so it's a very good method of electrochemical energy storage. However, shuttling causes capacity degradation, and so studies have looked into adding a hafnium oxide carbon nanotube layer that limits polysulfides to only the cathode side of the battery, as to not accumulate and cause that degradation. Experimentally increasing the coatings can help, but also will decrease at a certain point and has shown to optimize at 21 coats. Thank you for listening, and we hope you enjoyed our presentation.